So we know that chain length is going to be a very important parameter in classifying polymers and determining their macroscopic behavior. So here we're going to take a closer look at how we can quantify the molecular weight in terms of some average quantities. So remember that molecular weight is actually more correctly referred to as the molar mass. It's the total grams per mole of all the constituent atoms that make up a polymer chain. But it's very rare that a sample is going to contain chains that have all exactly the same length. A more realistic scenario is shown here, where we have a distribution of molecular weights across our sample. And the question then is, how can we come up with a parameter or a number that represents the average of this distribution? The first thing we can do is recognize that we can break this continuous distribution up into discrete bins where the width of this bar is the range of molecular weights, and the height of the bar is the number of the molecules in the population that have a molecular weight within that range. And you can see that as we add more and more of these bars, as they get thinner, narrower and narrower, we'll approach this continuous distribution function. So now the next question is, how do we compute an average? So I'm going to propose a general rule that if you just remember this, you can formulate any of these molecular weight averages that we're going to talk about, because there's more than one kind of average that we can use to characterize the molecular weight of the sample. So my rule is shown here. The x average y is equal to the sum over the distribution of x of each y times y over the total x. This probably looks kind of weird the way it's written right now, but let's see how we can apply it in terms of an actual example. So the number average molecular weight is an important kind of average that's often used to characterize these distributions. And this is abbreviated as m bar sub n. Now notice the way this is written, number average molecular weight. So if we compare that to my rule here on the right-hand side, number average, so number is x, and the average molecular weight, so y, corresponds to molecular weight. So if I apply this principle, then I can construct a relationship for the number average molecular weight that says that this is equal to the number of molecules of molecular weight mi times m sub I, the sum of this over the distribution, divided by the total number of molecules. So what I want to point out here is just how I constructed this relationship by following this general rule in terms of the average that I want to compute. Now let's see how we can apply this to actually get a relationship to help us calculate the number average molecular weight. Okay, so remember again, we have a distribution of chain lengths in our sample, or molecular weights, and we're breaking that up into discrete intervals. And we have this general equation for the number average molecular weight. So in this example, I have eight bins or 8 bars that represent the shape of this distribution curve. So on the x-axis, I have 8 different molecular weight ranges. So I'm going to call those M1, M2, up to M8. And the number of molecules that have that molecular weight represents the height of each bar. So I'm going to call those N1, N2, N3, and so forth. So if I plug that into this equation, what I have is the sum over this distribution. So for the first interval, M1, I have the number of molecules of molecular weight M1. So that's N1, the height of the bar, times that molecular weight at that interval, M1. So this is N1 and this is M1. Then I have my next interval, M2. So I have the number of molecules that have molecular weight M2. That is N2 times the molecular weight M2. And so forth. So I think you can see how this repeats over all 8 intervals. Then in the denominator, I have the total number of molecules. So I'm going to add up the heights of all of these bars, N1 plus N2 plus N3 plus all the way up to N8. That gives me the total number of molecules in my sample. So then I can rewrite this into a more mathematical form as shown below. We see that the number average molecular weight is the sum of the NIMI, or the product of the height of the bar times the molecular weight associated with that interval, across all the intervals, times the sum of the number of molecules in all the intervals, the total number of molecules. And this gives me what's called the number average molecular weight. So this is actually the same as computing a class average for an exam distribution. You have each grade, you have a distribution function like this of grades. So each of these would be the grades, 80, 85, 90, 95. And then on the y-axis, you have the number of students that score each grade. So then to compute the class average, you multiply the number of students that scored each of these intervals times that grade, divided by the total number of students, and you get the class average. So it's the same kind of average that we're talking about here, and that's the number average molecular weight.